Hello and welcome to this video lecture. In this lecture, we're going to bring together the different ideas that have been floating around when it comes to solving LTI ODEs. So we have the perspective from the approach associated with the characteristic equation. We also have the approach associated with the linear differential operator. So it turns out, and we clearly saw the similarities there, it turns out that there is a way that we can essentially bring those two concepts together. And in order to do so, we need to essentially develop a new mathematical space for us to work in. And that's the point of what we will start discussing today, or in this lecture, the Laplace transform. And so the Laplace transformation, or transform, and here I'll just abbreviate it as LT, is the thing that creates that new space for us. It maps what we're dealing with in our usual spaces, generally for us as engineers, what's happening in time, but it can also be associated with what's happening in space. And it allows us to map that into a new space. And so let's go ahead and capture that. So this is a transformation that, for our purposes, will take a function from, and here I'm going to be focused on time, from what we call the time domain, which is of course the space that we're generally familiar with, and it will map it to something in what we will call the S domain, to be technically correct, though generally the S domain is called the frequency domain, even though, and we'll discuss that later, even though the frequency domain isn't exactly the right term, but nonetheless it is one that is frequently used, very commonly used, when we're discussing this kind of transformation. So I'll generally be saying frequency domain. I might slip in some S domains there, here and there. In this particular discussion, just understand that the two are synonymous. So we're effectively mapping something from the time domain to something in this new space, this other space that's called the S domain or the frequency domain. So in order to do that, clearly we need to understand what that transformation is. So the definition of the, and here I'll spell it out one more time, of the Laplace transform is f of s, which is our transformed representation of the function, is equal to the integral from 0 to infinity of e to the negative st times f of t, where f of t is, of course, the function that we're starting with in the time domain. F of s is the function in the s or frequency domain, and all that times dt. Now, another way that we can represent this is usually using a script L, and then we can say that the Laplace transformation is being performed on this function of time. And so that's another way that we can write it, just to explicitly bring in this idea that this capital F of S is associated with the Laplace transformation. So let's go ahead and capture some of that. Specifically, I'm going to focus on the functions here. So F of t is the time domain function. And F of S is the equivalent S domain or frequency domain function. And so we have this new space that we're working in, this S domain, and you'll see very quickly how powerful the S domain is, and you're going to see, and how powerful this transformation is, and you're going to see that the discussions that we had associated with the characteristic equation and the linear differential operators essentially merged together in this space. So we saw how powerful each one was separately. Now we're going to actually be able to take those two separate threads, two separate lines of discussion, and we're going to be able to merge them together using this transformation. So let's go ahead. And so you can see that those discussions were effectively building up to this particular point. So let's go ahead and note something about the notation that hopefully you've already started to recognize, that of course the lowercase letters are used for the time domain, or if you prefer, the space domain if you're working with some kind of spatial function. So that's in the time domain, and of course the capital letters are used to represent the transformed function. So here I'll just say to denote the S domain function. So I've already started to discuss some of the important aspects, properties if you like, associated with the Laplace transformation, bringing these two related but what appeared to be separate lines of discussion together. But again, we can reiterate the properties that were associated with those two separate lines because, of course, they apply here as well. And so we'll see how powerful it is to transform into this new S domain, this new space in and of itself. We'll see why that is very helpful. But nonetheless, one of the very practical reasons for working with this transformation So here I'll say beyond just transforming for the sake of transforming, which is interesting in and of itself. So here I'll say beyond transforming from the time to the frequency domain or S domain. Generally I'll write S domain though, because it is a little bit faster. The Laplace transformation, again, has a very practical purpose, as we have pretty much started to see from our other discussions, because it allows us to express. So we've been seeing that we can work with the linear differential operator and kind of see that things might be happening algebraically, but now we're going to go ahead and formalize that we can express the differential equation or differential equations as algebraic. Equations. Now, it's important to recognize that this is a property of the transformation and a very important property, but it is clearly not the only property associated with the transformation. This transformation is a very rich transformation. There's a lot going on. There are a lot of properties associated with it, very useful properties associated with it, and we'll discuss one of those a little bit later. So let's just go ahead and kind of work with this first very important property that I just mentioned, that we can work with a differential equation essentially in an algebraic fashion once we have mapped that differential equation over into this new space, this S domain or frequency domain. So it turns out, and we'll work through the development to show you how this all works, that when we have a first order derivative, we just multiply that first order derivative just like we were talking about, or I shouldn't say just like, but in a similar fashion for what we were talking about with the characteristic equation. You see a first order derivative, you have S, and you go ahead and you take that S, and that S is multiplied by the transformed function x of S. So x, little x in this expression represents what's going on in the time domain. Capital X represents what's going on in this frequency domain. So of course, if we're transforming this differential equation, this X just gets transformed straight on across. And so we get the derivative. For the derivative, we multiply by S. We have our X of S, and then we have plus 3 times capital X of S, because that just transforms straight on across, and that's equal to 0. And so you can start to already see the merging of the characteristic equation approach and the linear differential operator approach, because this looks like what we would get when we're using the linear differential operator. But it turns out that we are also working with characteristic equations. So then we can write this as S plus 3, because we can, of course, factor out. Remember, we're now able to use our algebraic operations And so we can factor out that x of s, and that's of course equal to 0 for this homogeneous differential equation. One thing that I do want to mention is, and let me, instead of using that, let's use this. Note in this particular case, and you'll see why this is an important note later on, here I am assuming zero initial conditions, zero ICs in this particular case, or in this case, since it's a first order, zero, a single initial condition, which is 0. Now, we can see that the Laplace transformation will allow us to work with the differential equation as an algebraic equation, but it also has, as I indicated, other properties associated with it, and I like to call this effectively, this transform gives us effectively a one-stop differential equation. Here I'll do diff EQ solution shop. So the wonderful thing about this transformation is that, and I'll talk about a limitation, a couple limitations associated with it in a moment, but it effectively does everything for us when we work within those limitations. And so what do I mean by a one-stop differential equation shop? Because it turns out that these transformations will do just about everything we want them to do. They'll capture, it turns out, the particular solution, the homogeneous solutions, and in the form that we want them in, not only as a linear combination, but it will already figure out what's going on with the constants to capture the initial conditions or boundary conditions, depending on what kind of problem you're working with. So you can see how powerful this is. Instead of going and saying, okay, I'm now going to find the homogeneous basis functions, and then I'm going to go find the particular solution using the method of undetermined coefficients potentially, and then I'm going to go back through and solve for the arbitrary constants that give me the proper initial conditions, and going through this, each of those steps. This particular transformation just allows us to take care of everything all at once. Now, as I said, a couple limitations. One of the first limitations is that it will only do this for linear time invariant ordinary differential equations. So that's what we've been discussing now for quite some time, so it shouldn't be a surprise that this is one of the limitations. But nonetheless, don't try to use this where we have variable coefficients, even if it's linear, that this can't really handle variable coefficients, and it's certainly not a way to approach nonlinear differential equations. So it's only good for these LTI ODEs. Now, one other constraint is where we have time domain functions that meet, so this can only be applied to time domain functions that meet a particular requirement. Here I'll say the following condition. And that condition is that when we take the limit as the independent variable, here I'll just keep working and you can see my bias towards time domain issues or time domain analyses. So I hope you don't mind. We're just going to keep running with time as being the independent variable. So the limit as time goes to infinity, so as we go infinitely far out in time, when I take that time domain function and I multiply it by e to the negative sigma t, well, specifically take the absolute value of it, that needs to go to 0. And that has to be true for some positive constant. Sigma. So essentially, this is saying that when we're working with some function and we multiply it by e to, so you can look at it two ways. You can look at it in the way that we can test the function against this criterion and say, okay, we'll take the function multiplied by this e to the negative sigma t, and we'll see what happens as time goes to infinity, and it should go to 0. Or we can see it the other way. Instead of a test, we can see it as a requirement. And so since we will never work with time domain functions that violate this requirement, we can just assume, regardless of what the time domain function is, other than it meets this requirement, we can assume that this holds true. And that's extremely powerful because it turns out that at certain points when we're working with the Laplace transformation, we won't know what the time domain function is, and we'll end up in a little bit of a quandary where it's like, oh, well, we got this thing that we don't know what to do with it, until we say, oh, okay, we have this assumption. We have the, well, not even an assumption, a limitation. We are applying this limitation. And since we have this limitation, we can say that this happens. So this is a way for us to kind of get out of a little bit of a pickle that we get ourselves in when we're developing certain, how should I say it, certain relations associated with the Laplace transformation. Now, because this is important, we will say that we will only deal with time domain functions, of course, that satisfy this requirement, even though we may not know what that time domain function is, we're just going to say, well, it doesn't matter what it is, you are not going to violate this limitation. And these time domain functions, but let me get requirement down first. And these time domain functions are said to be of exponential order. And so essentially what it's saying is that if I take this time domain function and I multiply it by this particular function e to the negative sigma t, and I can go ahead and choose some positive constant sigma, that when time goes to infinity, that e to the negative sigma t overrules f of t and will drive f of t, regardless of what it is, will drive it to zero, because of course what happens as time goes to infinity, this exponential function tends to go to zero. So it's saying that this exponential function goes to zero when we're looking at the product, if you want to kind of think about it this way, that this exponential function goes to zero faster or fast enough that this time domain function, regardless of what it's doing, whether it's going to zero itself or whether it's trying to go to infinity, like a line might try to go to infinity, that exponential function is going to zero. How should I say it? I'll say it faster, is going to zero in a faster way than f of t is possibly growing to infinity. And so this exponential function will overwhelm the time domain function and will essentially drive it to zero. That's what we're saying when we're dealing with a function of exponential order. Now, you might ask, well, how does this make sense? So let's go ahead and see that when we are dealing with something like, and here I'll just do a little aside. There we go. So you might say, well, okay, Professor Dinsmore, that makes sense. But how do we end up with a function that isn't of exponential order? Well, let's go ahead and look at an example where this works out and where we are dealing with a function of exponential order and one where we are not. So let's say that we have f of t being equal to e to the at, where a is, well, let's make it a bit more specific. Let's do e to the 3t. And so then we can say that e to the negative sigma t times e to the 3t, well, that's equal to e to the 3t minus sigma t, otherwise known as e to the 3 minus sigma t. And can I choose a positive value of sigma that drives this, what originally was a product, but now everything is in the argument, that drives this particular new function to zero? And the answer is, of course I can. I can just choose sigma being equal to 4, then I get e to the negative t, and then as t goes to infinity, obviously that goes to 0. So yeah, I can go ahead and find a sigma that will drive that to 0. And so that means that e to the 3t is of exponential order. Not a problem. How about, though, if f of t is equal to e to the t squared? Okay, well, let's just do the same thing. We have e to the negative sigma t times e to the t squared. Obviously, that's equal to e to the t squared minus sigma t, which is, of course, equal to e to the t minus sigma times t. And we can see that since this t here is constantly increasing all the way off to infinity, because we can go infinitely far down, and well, we have to for this particular assessment, we have to take t to infinity. Can I choose a value of sigma that will give me a negative value in this quantity? And the answer is clearly no. You give me any value of sigma, I'll just wait a little bit longer in time, and my time will go beyond that value of sigma. And so I will always be able to beat out whatever quantity of sigma you choose. I'll just wait longer. And so we can see that this won't map to 0 as t goes to infinity. And so that means that e to the t squared is not of exponential order. So let's go ahead and get that down. So this first function that we are dealing with is, of course, of exponential order, and so we can work with the Laplace transformation of e to the 3t. The second one, of course, is not of exponential order. And so we can't work with that in this space. So we can't deal with the Laplace transformation of e to the t squared. It just won't work out that way. So hopefully this discussion has given you a chance to see what the Laplace transformation is, how it actually gives us a similar form. We'll go ahead and push the discussion a bit further because I just showed you the Laplace transformation of a differential equation. I didn't get into how it actually, or how we can actually see that the Laplace transformation will do that, and that's what I'll do in our next lecture. We can see how the Laplace transformation is really working with the threads that we have developed before with the characteristic equation and the linear differential operator, but it's doing it in a different way through the context, through the lens of this transformation, this Laplace transformation. But even with that, we can see that the Laplace transformation has limitations. Again, like we were working with these expressions before, it can only deal with LTI ODEs, and it can only work with these expressions, these functions of time that are of exponential order. So in the next lecture, we'll go ahead and start using the Laplace transformation to develop general expressions for particular operations and or functions. So with that, though, having introduced the Laplace transformation and its limitations and giving you an idea of some of its properties, I will go ahead and call this particular video lecture a wrap.